At the end of this video, you should be able to determine the formula of an ionic compound formed between two given ions and name an ionic compound given its formula. Chapter 7, Section 1, Monatomic Ions. By gaining or losing electrons, many main group elements form ions with noble gas configurations. For example, group 1 metals lose 1 electron to give 1 plus cations, such as the Na plus cation. Group 2 metals lose 2 electrons to give 2 plus cations, such as Mg2 plus ions. Ions formed from a single atom are known as monatomic ions. The nonmetals of groups 15, 16, and 17 gain electrons to form anions. For example, in ionic compounds, nitrogen forms the 3 anion N3-. The 3 added electrons plus the 5 outermost electrons in the nitrogen atoms gives a completed outermost octet. Similarly, the group 16 elements, sulfur and oxygen, form 2 anions, and the group 17 halogens form 1 anions. Not all main group elements readily form ions, however. Rather than gain or lose electrons, atoms of carbon and silicon form covalent bonds in which they share electrons with other atoms. Other elements tend to form ions that do not have noble gas configurations. For instance, it is difficult for group 14 metals, tin and lead, to lose 4 electrons to achieve a noble gas configuration. Instead, they tend to lose the 2 electrons in their outer p orbitals, but retain the 2 electrons in their outer s orbitals to form 2 plus cations. Tin and lead can also form molecular compounds in which all 4 valence electrons are involved in covalent bonding. Elements from the D block form 2 plus, 3 plus, or in a few cases, 1 plus or 4 plus cations. Many D block elements form 2 ions of different charges. For example, copper forms plus 1 cations and 2 plus cations. Iron and chromium, on the other hand, each form 2 plus cations as well as 3 plus cations. And vanadium and lead form 2 plus, 3 plus, and 4 plus cations. Naming monatomic ions. Monatomic cations are identified simply by the element's name, as illustrated by the examples on the screen now. Naming monatomic anions is slightly more complicated. First, the ending of the element's name is dropped. Then the ending IDE is added to the root name, as is illustrated by the examples on the screen now. The names and symbols of the common monatomic cations and anions are organized according to their charges in Table 7-1 on page 205 of your text or on the screen now. The names of many of the ions in the table include Roman numerals. These numerals are part of the stock system of naming chemical ions and elements. You will read more about the stock system and other systems for naming chemicals later in this chapter. Binary ionic compounds. Compounds composed of 2 different elements are known as binary compounds. In binary ionic compounds, the total numbers of positive charges and negative charges must be equal. Therefore, the formula of such a compound can be written given the identities of the compound's ions. For example, magnesium and bromine combine to form the ionic compound magnesium bromide. Magnesium, a group 2 metal, forms the Mg2 plus cation. Note that the 2 plus in the Mg2 plus is written as a superscript. Bromine, a halogen, forms the Br minus anion when it is combined with a metal. In each formula unit of magnesium bromide, 2 Br minus anions are required to balance the 2 plus charge of the Mg2 plus cation. The compound's formula must therefore indicate 1 magnesium 2 plus cation and 2 bromide minus 1 anions. The symbol for the cation is written first. The ions that are combined, Mg2 plus, Br minus, and Br minus. The chemical formula is written MgBr2. Note that the 2 in the Br2 is written as a subscript. The charges of the ions are not included in the formula. This is usually the case when writing formulas for binary ionic compounds. As an aid to determining subscripts and formulas for ionic compounds, the positive and negative charges can be crossed over. Crossing over is a method of balancing the charges between ions in an ionic compound. For example, the formula for the compound formed by the aluminum ion, Al3+, and the oxide ion, O2-, is determined as follows. 1. Write the symbols for the ions side by side. Write the cation first. 2. Cross over the charges by using the absolute value of each ion's charge as the subscript for the other ion. 3. Check the subscripts and divide them by their largest common factor to give the smallest possible whole number ratio of ions. Then write the formula. Multiplying the charge by the subscript shows that the charge of the two Al3+ cations, 2 times 3 plus, is equal to 6 plus, equals the charge on the 3 O2 anions. 3 times 2 minus is equal to 6 minus. The largest common factor of the subscripts is 1, so the correct formula is therefore Al2O3. Naming binary ionic compounds. The nomenclature, or naming system, of binary ionic compounds involves combining the names of the compound's positive and negative ions. The name of the cation is given first, followed by the name of the anion. For most simple ionic compounds, the ratio of the ions is not indicated in the compound's name because it is understood based on the relative charges of the compound's ions. The naming of a simple binary ionic compound is illustrated by aluminum oxide, Al2O3. So as we take that information that we now have, where the positively charged ion just keeps its same regular name, in these examples it's silver, calcium, potassium, and then sodium, we don't change the name. It's the negatively charged ion that we drop the last syllable and we add IDE. So silver and fluorine becomes silver fluoride. Calcium and chlorine becomes calcium chloride. Potassium and oxygen becomes potassium oxide. Sodium and bromine becomes sodium bromide. Also, please notice that whenever there's an opportunity for like charges, should I say like magnitudes, there's just one of each, no problem. But if we have like a calcium, which is a +2, with chlorine that is a -1, we require 2 of the -1s to balance out the +2, or conversely, 2 of the +1s to balance out the -2. The stock system of nomenclature. Some elements, such as iron, form 2 or more cations with different charges. To distinguish the ions formed by such elements, the stock system of nomenclature is used. This system uses a Roman numeral to indicate an ion's charge. The numeral is enclosed in parentheses and placed immediately after the metal name. Names of metals that commonly form only one cation do not include a Roman numeral. There is no element that commonly forms more than one monatomic anion. Naming a binary ionic compound according to the stock system is illustrated on the screen now. Once we understand what the stock system of nomenclature is used for, it's very easy to see when it should be used and when it shouldn't. We now understand that there are certain metal cations that form multiple charges. We see lead here and lead here. One is a +2 charge, one is a +4 charge. In general, these are far too cumbersome to simply memorize every version of them, and so we use the stock system to aid ourselves. So, and notice that these are going to be all transition metals. D block metals, these, especially in these examples. So we have tin. Tin can form +2 charge or a +4 charge. How do I know which charge it is in this particular compound, I write tin and Roman numeral 4 in parentheses. That indicates that the tin has a +4 charge. Now, in order to balance out that +4 charge, I need 4 species of the -1. So we say tin 4 iodide. Copper, this particular copper is the kind that has a +2 charge. So we say copper 2 chloride. This type of lead is the lead that has a +2 charge, so we say lead 2 oxide. Lastly, this type of lead has a +4 charge, so we say lead 4 oxide. Now notice we have a different set of oxygens. We have PbO and then PbO2, which makes sense because this lead only has a +2 charge, so in order to balance that out, we only need 1 -2. This lead, however, is a +4 charge, so we need 2 oxides, each at -2, to balance out the lead 4. But notice that there is no difference in how we say oxide. The difference lies in saying lead 2 oxide and lead 4 oxide. Compounds containing polyatomic ions. Table 7-2 on page 210, or on the screen now, lists some common polyatomic ions. All but the ammonium ion are negatively charged, and most are oxyanions, which are polyatomic ions that contain oxygen. In several cases, 2 different oxyanions are formed by the same 2 elements. Nitrogen and oxygen, for example, are combined in both NO3- and NO2-. When naming compounds containing such oxyanions, the most common ion is given the ending ATE, 8. The ion with one less oxygen atom is given the ending ITE, ite. Sometimes 2 elements form more than 2 different oxyanions, and in this case, an anion with one less oxygen than the ite anion would be given the prefix hypo. An anion with one more oxygen than the 8 ATE anion is given the prefix per. This nomenclature is illustrated by the 4 oxyanions formed between chlorine and oxygen. Compounds containing polyatomic ions are named in the same manner as binary ionic compounds. The name of the cation is usually given first, followed by the name of the anion. For example, the 2 compounds formed with silver by the nitrate and nitrite anions are named silver nitrate, AgNO3, and silver nitrite, AgNO2, respectively. When more than one polyatomic ion is present in a compound, the formula for the entire ion is surrounded by parentheses. This is illustrated on page 204 of your text or on the screen now for aluminum sulfate, Al2SO4 The formula indicates that an aluminum sulfate formula unit has 2 aluminum cations and 3 sulfate anions. At this point, you should be able to determine the formula for an ionic compound formed between 2 given ions and name an ionic compound given its formula.